Hello everyone, welcome to this new session. So in the last session we have discussed briefly we have discussed all the concepts of stability analysis using RH criteria, right? So in the upcoming few sessions we are going to solve many problems and very interesting problems. So you will understand it very briefly. So let's get to the first problem now. Okay, that is analyze the stability of the system using RH criteria for having the characteristic equation. They have given it as s to the power 5 plus s to the power 4 plus 2s cube plus 2s square plus 3s plus 5 equal to 0. Okay, so now for this, how many roots of the equation are on the imaginary axis and on the right half of the S plane? Okay, so that directly they have not given to stability. Okay, they have enough after stability analyzing we need to check how many roots of this equation are on the imaginary axis and right half of the S plane. Okay, so if they in the question they have asked that how many roots are in the right half of the S plane, we know that whenever the roots are in the right half of the S plane, the system is unstable in nature, right? So directly if there is no root in the right half of the S plane, we can say that the system is stable. Okay, and also imaginary axis means the system should be marginally stable for that. Okay, so it's not possible in this case since we are not getting any marginal values. So we need to be checking if we are getting any row of zeros in this question. Okay, so in this question, if while we are solving, if we get any row of zeros, then there are chances that the system is marginally stable and the roots might be on the imaginary axis. So that won't be there in this question. So we can directly conclude that there are no roots in the imaginary axis in this question. Okay, so now let's solve this question. So now let's write the route array for this. Okay, start from s to the power 5, s cube, s square. So write it like this. And after that, what to do? First write the coefficient of s to the power 5, that is 1. Then leave one term and write the coefficient of s cube, that is 2. Again leave one term, write the coefficient of s 3, and again leave one term. After that we don't have any terms, so 0. Okay, so here write the coefficient of s to the power 4, this is 1. Okay, leave one term, s square coefficient 2, leave one term, the coefficient of s to the power 0 is 5. Again we have don't have any term, 0. So now in order to find the third row elements, use the previous two rows. So first you 1 into 2 minus again 1 into 2 divided by 1, so that's equal to 2 minus 2 by 1. So 2 minus 2 is 0, so here we are getting 0, right? So see here directly in the while seeing in the, if you observe that in the first column we have got the one element as 0, right? So we need to be using one method, right? That is epsilon method, or replacing s by 1 by z method. So here I'm going to use epsilon method. So before that, let's solve for this element, that is 1 into 3 minus 1 into 5 divided by 1, that is 3 minus 5 by 1, that is equal to minus 2. So right here minus 2, and here we would be getting 0. Here is also again it's 0 only. So now here we got 0, right? So replace 0 by epsilon as I've told you, and again solve using epsilon only. So epsilon into 2, that is 2 epsilon. 1 into minus 2 is minus 2, so we have minus, so this would be plus 2 by epsilon. So here we need to writing 2 epsilon plus 2 by epsilon, right? And here epsilon into 5 minus 0 divided by epsilon, so that is 5 epsilon by epsilon. Epsilon gets cancelled, the remaining value is 5. So here it is again 0. So now these two we need to be multiplying in order to get this element, that is 2 epsilon plus 2 by epsilon into minus 2 divided by 2 epsilon plus 2 by epsilon. So multiply minus 2 this to this term, that is minus 4 epsilon minus 4 divided by epsilon. So here we missed one term, that is minus epsilon into 5, right? 5 epsilon. Okay, minus 5 epsilon divided by 2 epsilon plus 2 by epsilon. So we can cancel this epsilon after taking LCM, that is minus 4 epsilon minus 4 minus 5 epsilon square, right, if we multiply, divided by 2 epsilon plus 2. So okay, this we need to be writing now. So this term, write it here now, that is first write the highest coefficient, minus 5 epsilon square minus 4 epsilon minus 4 divided by 2 epsilon plus 2, and here we will be getting it as 0, and again this term into this term multiply, that is 5 epsilon square minus 4 epsilon minus 4 divided by 2 epsilon plus 2 into 5, and here if you multiply 2 epsilon plus 2 into 0, it is 0 again. So the answer is 5 minus 5 epsilon square minus 4 epsilon minus 4 divided by 2 epsilon plus 2 minus 0, sorry, minus 0. So now I will again summarize what and all I have done. Okay, so here I have taken this term, so applying all the limits one by one, what we will be getting, split this 2 epsilon by epsilon plus 2 by epsilon, cancel epsilon, so you will be remaining only with 2, then apply the limits, that is epsilon tending to 0, so 2 by 0 is infinity, so 2 plus infinity, we know that infinity plus any number is infinity only, so here I have replaced this term by infinity, I have written here plus infinity, and again for this term apply the limits again, so 5 epsilon square minus 4 epsilon minus 4 divided by 2 epsilon plus 2, okay, then apply the limit, so epsilon wherever is there it is 0 0, so all the epsilon terms will be getting cancelled, so the remaining terms are constant terms, minus 4 divided by plus 2, that is minus 2, so now in place of this term I have replaced it by minus 2 and I have rewritten the Raut array here, okay, and rest all the terms I have written as it is, and also you can see that after rewriting the Raut array, check the first column, okay. So here the sign changes are, you can see here, so wherever this is 0, right, so we have replaced 0 by epsilon, so in place of 0 we need to be writing epsilon, okay, here plus infinity, after substituting the limits, here we got minus 2 and 5, so you can see that from plus to minus we have one sign change here, and from minus to plus we have one sign change here, so there are two sign changes in this question, okay, so we can say that the system is unstable, so I have written system is unstable, and also since while solving this problem we have not got any row of zeros, right, so here we can say that the system is not marginally stable, therefore no roots are on the imaginary axis, and also they have in the second sub question they have mentioned how many roots are on the right half of the S-plane, okay, so since we got here two sign changes, so we can conclude that two roots, okay, since two sign changes, so two roots, and since the system is unstable, these roots are on the right half of the S-plane, so therefore we can conclude that there are two roots on the right half of S-plane, okay. So this was this problem here, so please refer this problem very carefully, this is a very important problem. So this is the fourth question and very important question related to root locus only, that is we need to analyze the stability of the control system with the given open loop transfer function as k into s plus 6 divided by s into s plus 2 using root locus technique. Also they have given one condition that we need to show that a part of root locus which is obtained when we part of root locus which you obtain in the finally is a circle of radius, they have mentioned it as square root of 24 units with center at minus 6 comma 0, okay. So this is the question, we need to prove this part, okay, whatever root locus which you obtained at last, it should satisfy this condition given, okay. If we don't satisfy, if the root locus obtained is not satisfying this condition here they have mentioned, then we might be doing some mistakes, okay, when we have done some mistake, okay. So that's why please see the question very carefully and try to obtain the condition given here. So now let's solve it. So the first step is write the transfer function given, that is g of s into h of s is equal to k into s plus 6 divided by s into s plus 2, okay. So now step 1, we need to be finding number of poles and zeros. So here zeros, in this case we have 1 zeros, that is s plus s is equal to minus 6, and poles we have two poles, one is at 0 and one is at minus 2, okay. So the zeros are s is equal to s plus 6 equal to 0, so s is equal to minus 6, and the poles are one is at 0 and one is at minus 2. Okay, so that's why now we need to be finding number of loci is equal to maximum of p comma z. Okay, so that's equal to maximum of 2 comma 1. Since we have the greater number of poles as 2, so that's why our number of root loci we are getting that is equal to 2. So we are going to get two separate branches of root loci. So step 2, number of asymptotes, that is number of straight lines which is made by the root locus. The formula is number of poles minus number of zeros. So poles are 2 and zeros are 1. So number of asymptotes obtained is 1. So here we have only one single asymptote. So when we have one single asymptote, the angle of asymptotes also we are going to get one single angle of asymptote. That is the value of q. Only we can substitute the value of q is equal to 0 only in this case, because we have only one single angle. So that angle obtained is obviously 2 into 0 plus 1 into 180 degree divided by p minus z, that is 2 minus 1 is 1. So that is 180 degree divided by 1, that is equal to 180 degree only. So here we see the angle again which we have got is similar to the angle which we have got in one previous problem which we have solved, that is 180 degree. Since it is only one single angle of asymptote, so that's why the angle is also 180 degree. So it is with respect to real axis. So if we don't draw that angle also, it's of no use. But whenever we get one single angle that is equal to 180 degree, then the centroid obtained in most of the cases would be positive only. Okay, so now let's see that whether we get the centroid as positive or not. Okay, yeah, so this is the formula for centroid: summation of real part of poles minus summation of real part of zeros divided by number of poles minus number of zeros. So real part of poles, since we are obtained only real poles, so that's why the real part of poles is minus 2, minus of 0 is 1, we have obtained it as minus 6 divided by p minus z is 1, so that is minus 2 plus 6 by 1, that is equal to minus 2 plus 6 is plus 4. So here a sigma obtained is positive here. So that's why we know that we have a condition for sigma, it should be strictly less than 0, but we have one positive sigma. So in this plot there is no centroid which exists, so that's why there is no angle of asymptote as well. But also if there is an angle of asymptote, it's 180 degree. It's what to say, you can ignore it since it is a straight line. So that's why this is the condition for centroid. So now let's calculate the breakaway point. So the formula is 1 plus g of s into h of s equal to 0, 1 plus k into s plus 6 divided by s into s plus 2 equal to 0. Okay, so that is 1 plus k into s plus 6 divided by s square plus 2s is equal to 0. So that is, if you cross multiply s square plus 2s plus ks plus 6k, that is equal to 0. So that's why s square plus, so we have here s common, so we can take 2 plus k together plus 6k equal to 0. So this is the characteristic equation obtained from this breakaway point. So now using this, let's compute the value of k. Bring this k term to one side, that is 6k is equal to minus s square minus of 2 plus ks. So that is equal to 6k is equal to minus s square minus 2s minus ks. So we can bring this since we have here one ks term, so bring that ks term also to other side, that is 6k plus sk equal to minus s square minus 2s. So we can group this term, that is k into s plus 6 is equal to minus s square minus 2s. So that's equal to k is equal to, we are getting minus s square minus 2s divided by s plus 6. So this is the equation obtained for k now. So now using this we can compute dk by ds equal to 0. So that is, we need to take the derivative. So in order to take the derivative here, it is of the form of u by v. So we need to be using the u by v rule. So it is denominator square, that is s plus 6 whole square, into numerator s minus s square minus 2s, differentiation of denominator with respect to s, so differentiation of s is 1, minus denominator s plus 6 into differentiation of numerator, that is minus 2s. Differentiation of minus s square is minus 2s and minus 2s is minus 2 is equal to 0. So if you bring this s plus 6 whole square to other side, that's also would be equal to 0. So minus s square minus 2s into 1 is the same, that is minus s square minus 2s minus of s plus 6. So here also we can take minus common outside, minus of 2s plus 2 equal to 0. So here these two are getting multiplied, so minus into minus is plus, minus s square minus 2s plus s plus 6 into 2s plus 2 equal to 0. Minus s square minus 2s, then 2s into s is 2s square, s into 2 is 2s, plus 6 into 2s is 12s, plus 6 into 2 is 12 equal to 0. So we can cancel minus 2s and plus 2s here. So now minus s square plus 2s square, that is equal to s square, plus the remaining term, that is 12s plus 12 equal to 0. So this is the quadratic equation which I have obtained. So now for this, let's find the roots here using the calculator, that is mode equation, that's of the form ax square plus bx plus c, so 3. Then substitute the coefficient, that is 1, 12 and 12. So the roots obtained are minus 1.1 the first root, minus 1.1 comma second root is minus 10.89, so we can round it off to 10.9. okay, yeah, so these are the two roots obtained here. So now we need to be checking whether these two are valid breakaway points or not, whether these two. For that we need to be drawing one rough plot again to check whether it's a valid breakaway point or invalid breakaway point. So this is the rough plot. One pole is at 0, one pole it at minus 2, and there is one 0 at minus 6. okay, so if you want to this to be valid breakaway point, so this 1.1 lies in this place. okay, so that is from this pole. If you look towards the right, we have only one pole, that is odd number of poles, so this is the part of root locus, but this value lies in this region, so this is the valid breakaway point 1.1. also this minus 10.9, from here if you look from 0, if you look to the right, we have two poles, right, that is even number of poles, so that's why this region is not the part of root locus. But also from infinity, minus infinity, if we look towards right, we have three poles, three quantities, that is adding 0 as well, we have 1 0 and 2 poles, we have 3 number of zeros and poles. If we together sum it up, we have 3, it is again odd number, so that's why this whole part here from this point 0 minus 6 to infinity, it is a part of root locus. okay, so that's why this minus 10.9 lies in this region, right, so that's why this is also a valid breakaway point. So these two roots are obtained, both are also valid breakaway points. So in this case we are going to have two breakaway points. okay, yeah, so next step again, angle of departure. So since in this case the roots are obtained are real roots, so that's why we no need of calculating any angle of departure for that. So now let's calculate the point of intersection. So this is the characteristic equation obtained. So for this equation, now we need to be writing the Routh array, s square, s power 1, s power 0. The coefficient of s square is 1. Skip this term, and coefficient of s power 0 is 6k, 0. Coefficient of s power 1 is 2 plus k. Then we don't have any terms, so 0. So using these two rows, try to calculate this term, that is 2 plus k into 6k minus 1 into 0 is 0 divided by 2 plus k. So these two gets cancelled, so remaining term is 6k. So now this is the Routh array obtained. So now for this we know that 6k should be strictly greater than 0. So that's why the above row element, that is 2 plus k, is replaced by k margin in order to become that row of 0. So we need to equate this term equal to 0. So our marginal value which we obtained is equal to minus 2. okay, so now using this marginal value, we need to substitute back in the auxiliary equation obtained above the row of zeros, that is a of s is equal to 0. The equation obtained is s square plus 6k, 6 into k margin, since k is replaced by k margin equal to 0, s square plus 6 into k margin obtained is minus 2 equal to 0. So s square minus 12 is equal to 0. S square is equal to minus 12, if you bring it to other side it will be plus 12. So s square is equal to, so s is equal to plus or minus square root of 12. So s is equal to plus or minus square root of 12 in general, what we are getting is 3.46. okay. So here this is the value of S obtained, but here you can see that this is not an imaginary value, this is a real value, plus 3.46 and minus 3.46. But this step here we are going, we were calculating for the intersection on imaginary axis, right? But here since we have got the real value, so in this case we can say that directly there is no point of intersection. I've told you that whenever we get the value of S as 0 or any real value, there is always no point of intersection, because we need to be getting the imaginary values in this case, okay. So we can directly write it as no point of intersection. So now using the data provided by the calculations, let's plot the graph and see whether we are satisfying the condition or not. And also we need to be analyzing the stability, right? So if we see the here in this case, we have one pole here, and one 0 here. All of them are coming in the left half of the S-plane, okay. So whenever it comes, whenever all the roots or zeros are in the left half of the S-plane, we can say that the system is stable, right, in general. So in the question also they have given to analyze the stability, so that's why that conclusion we can directly write is that system is stable, okay, in this case. Okay, even the reason also you can give, because all the roots are lying on the left half of S-plane, okay. So therefore system is stable. So in the question, since they have given to analyze the stability, so that's why I am writing it. Yeah, so now let's plot the graph. So this is the rough plot here, okay. So I have not written any values for imaginary axis because we don't have any point of intersection, right? So that's why the imaginary axis is of no use in this case. So now let's mark the poles here. So one pole is at origin 0 and the other pole is at minus 2, right? And we have one more 0 that is at minus 6. So mark that 0 as well, okay. So now we have got one breakaway, two breakaway points, because since from this pole, if you observe, we have here this region, so this region is a part of root locus, and from this 0 to this pole, this region is not a part of root locus, and from this E0 to infinity, the whole region also is a part of root locus. So that's why we are getting two breakaway points. One breakaway point is at minus 1.1, so it might be coming here somewhere, minus 1.1, and other breakaway point is at minus 10.9, right? So this is that breakaway point, minus 10.9. so these are the two breakaway points here. I've highlighted it, okay. So also in this case there is no centroid, so no angle of asymptote, so that's why it's not required. So now let's try to draw the root locus. Since here we have two breakaway points, we should be knowing that the branches should be approaching towards both the breakaway points. So how it might be approaching? That is, see, we have two poles here and we have one breakaway point between these two poles. So that's why we can say that from these two poles, these two poles are approaching towards the breakaway point in the opposite directions. And from here, it might be going upwards or downwards. It's your wish. You can write it as it is. This direction also it might be going upwards or downwards. And from this point, it would be diverging and it would be meeting this breakaway point, okay. But in the question they have mentioned the condition that we need to be getting a circle, right? So in a circular form we need to be drawing this branch here, okay. So from this point, let's draw one half semicircle which is touching minus 10.9, okay, and the direction is like this. And from this branch, let us assume that it's your assumption, okay. It might be anyway, even this branch is moving like this or this branch is moving like this. So now from this branch I am drawing one semicircle downwards, okay, and it is touching to the breakaway point here, okay, and the direction is moving downwards like this and it is approaching towards the breakaway point, okay. And these two branches now meet at this breakaway point, okay. So now we know that since we have one 0, one of the branches would be approaching towards 0 and terminating at 0, and one of the branches would be approaching towards infinity, because we have one angle of asymptote that is 180 degrees. So that's why it would be approaching towards that angle of asymptote, towards that direction only. That's why one branch would be approaching, it might be either this branch or this branch would be approaching towards 0, and from this point other branch would be approaching towards infinity. Okay, so this is the root locus plot obtained, and also the condition is they have given that we need to be getting our root locus, part of root locus, as a circle, right? So I've drawn it in the form of a rough circle with the center at minus 6 comma 0. See, I've got the same center here, that is minus 6 comma 0, right? From this center, and the radius also they have given as square root of 24 units, that is from this point till we have one breakaway point value we have obtained is minus 1.1. If we check the radius here from this point till minus 1.1, it is approximately we are getting is equal to minus, the radius is 4.9. okay, but in the question they have mentioned it as square root of 24. okay, so now let's check that let's check that square root of 24. So square root of 24, see, it's approximately 4.89. Round it up, if you round it up you would be getting 4.9. so from this center the radius we have obtained is 4.9, and also from this center the radius of this side also, see, from minus 6 to minus 10.9 the range is again 4.9. so that's why the diameter obtained is approximately equal to 10.8, and the radius is square root of 24, that's obtained, and they have given also from center minus 6 comma 0, and the radius is also obtained. So from this way we have proved that the part of root locus is a circle with center of minus 6 comma 0, and also the radius obtained is square root of 24 units. okay, and also we have proved that the system is stable. okay, since all the roots are on the left half of the plane, therefore the system is said to be stable. okay, so this is the root locus plot here. okay, so please analyze this problem and